Oh, hi everyone. How are you? Nice to see you all again today. We've got 140 people in the live stream, so that's about a quarter of the course has tuned in today. Um, some people on the chat are certainly more enthusiastic than is necessary. Though I dig the energy. Just they should direct it at your work. It'll be great. Um, Hi everyone. So I read through the lecture feedback from lectures 1, 2, and 3, and generally you were all very kind, which was nice. Though I think one thing that came up a bit was that people were like, oh, I'm still very confused about make files. Um, and you're right, we did go through that really quickly. Part of the reason was because we don't actually expect you to write make files yet. It's something that we're going to keep talking about in the course. It was more like a here is what it's about. Though I'm sympathetic that maybe people want to understand it some more. So we will talk about it a bit today. Um, Today's lecture, the only thing we have left from week 1 is recursion, which is a challenging topic. I just want to put that up in advance. It will be something that you will understand by the end of the course, but most of you will still walk away today, or a chunk of you, I should say, will be like, that's a little bit strange. But we're going to discuss it anyway, and we will do a little bit of make files as part of this, just so you can get your head around it. And if we're plenty good on time, we'll make a start on week 2's stuff. I don't know how long week 2 will take. Normally I would just end lectures early. I'm not like a person that's scared of ending lectures early. I don't think I need to make you endure pain, but just on the odd chance we need a lot of time next week, we might yeah, we might tackle that. William H says Ryan explained recursion really well in our tute. I know, I'm sure they did. All of your tutors are amazing. I think they're more incredible than me. So make sure you're going to your tutes, because they've been teaching this particular content often more frequently than I teach it. So you're likely to get some really good explanations from some of your tutors. So you should definitely go and attend your tutorials. And for those of you as well, you've probably noticed that a bunch of tutes actually happened before our lectures, but we've kind of made sure that from week 2 onwards and stuff that we don't, how would you put it? That we don't kind of put things on you that you haven't learned yet. So for instance, I think by design, we've made sure that everything about, like you're not relying on content being taught that week, if that makes sense. Yes, that is the chair. Okay, so let's talk about recursion. There's a very short set of slides, because it's actually just going to be talking about code quite a bit. We'll do some compilation of the code, and then at the end we'll come back and we'll talk about make files and how that fits into this. But again, why are we doing this lecture right now? Well, you don't actually need recursion to solve a lot of problems. There are most problems that you solve in computer science use for loops for, right? Like there's a general notion of looping that helps you solve a problem. Recursion is kind of an alternative to using for loops and while loops, is maybe a really simple way of explaining it. And it's not critical. Like you can do most things in life without it, but it does make certain programs a lot easier to write, a lot easier to understand. It doesn't necessarily make your code faster. Very rarely will it actually make your code faster, but what it's certainly going to do is make your code more understandable in some cases. And we will see this come up more in week 3 and on. We're just talking about it now to introduce the concept to you. And there's a few fairly standard examples we're going to go through, which you would have seen online. So first thing is, what in God's name is recursion? Recursion is a programming pattern where a function calls itself. So the name is somewhat indicative of what it is. If you have a function that inside the function actually calls itself, then that's what we call a recursive function, or a function that is using recursion. I don't know what happens if we Google recursion. The repeated application of a recursive procedure or definition. I hate it when definitions use their own word in that. But yeah. There's lots of good explanations online, because it's quite a straightforward concept. And if you're struggling to like even think about recursion, what's really cool is that when I just even Googled it, you'll actually see some really tactile understandings of recursion, which are I saw like this is recursion, right? Like this is an image that displays itself, which is an image that displays itself. You've all kind of seen things like this, whether you realize it or not. like these triangles, right? It's a triangle made up of triangles, right? That's like what it is. So when we say it's a function that calls itself, it's the same thing, right? Like this is a triangle that draws itself by making more triangles, and those triangles are made up of more triangles, etc., etc., etc. Whereas here, we're talking about functions that call themselves. So typically, as I mentioned, recursion replaces some kind of looping. This is a very general rule. I wouldn't say this is a hard definition. I would say this is just an easy way to explain it to you. So typically, you'll have a lot of programs that will loop through things, like looping through a list is the simple example. And as we get further into the course, we'll see far more complex ones. But generally speaking, it's replacing loops. So what we've actually got here is a really simple program to calculate the factorial of something. So if you remember this from, high school, if I go to like, Wolfram Alpha, I remember when this site was released, it was so cool. And I type in 8 factorial, which hopefully you all know from whatever, from high school. Oh, it doesn't really show us here, which is a shame. But 8 factorial we know is equal to 8 times 7 times 6 times 5 times 4, right? Like that's what factorial means. So if we want to write a programming function that takes in that number 8 and it calculates the factorial for us, I could have probably given that to you now, and you would be able to write something like this. You would be able to write something where you say, okay, well, I've got a main function that's literally just going to print out the result of calling. Sorry, that's just a bug in my code. Yeah, that should say factorial. I'm sorry about that. But very quickly update that so I don't confuse you. Again, most of the first 2 weeks are new slides. Like I kind of rethought some early parts of the course, so I think there's just going to be a couple of tiny little mistakes in them. But I just want to fix this one up because it's the first example. Factorial, and then we just refresh this page, and it should be fine. It's still updating. There we go. Okay, so essentially we just have a main function here, and all that main function does is actually call the factorial function with a number, in this case 8, and then the factorial function calculates it for us. Now this one is pretty straightforward. We start off with a product, a number 1, and then we loop through from 1, 2, 3, 4, 5, 6, 7, 8, and then we just multiply that same number. So we start off with 1 times 2 is 2, 2 times 3 is 6, 6 times 4 is 24, right? Times 5 is 120, times 6 is 720, like that, right? All the way through till whatever the hell 8 factorial is, 40,000 or something, right? 40,320. So it's a pretty straightforward function. If you don't understand it, that's totally okay. Anytime I kind of say to people like it's a fairly straightforward thing, I'm not saying that there's an expectation that you understand everything off the bat. It's more like a standard student who has done like a Comp 1511 last term will have a relatively okay understanding of it just by looking at it for half a minute and being like, ah, yes, I see what that one's doing. And let's actually just try and run this. Like let me really take you through this bit by bit. So I'm just going to open a terminal. We're going to go to CS2521. I might make a folder for 1.2 or like 1.4, I guess, which is the lecture we're in. And then we'll open gedit and we'll paste this in. So I'm going to call this one factorial1.c, which we'll store in 1.4. And I'm going to compile it. Now, if like we talked about compiling, so let's just quickly revise that. We've got like dcc factorial1.c -o factorial. Actually, let me just simplify this terminal. Okay, so you might have again been doing this in 1511, or alternatively you might have done this, which are both the same thing, right? They're just the different order of the commands. And then you might run it like you might run factorial like this, right? And then you get 4320. Now, let's compile this with GCC, which is what we did last lecture. So what are the differences? Well, firstly, I could just replace DCC with GCC, and you'll see it will compile the same and it will run the same. Generally speaking though, when we compile something with GCC, we usually compile it with a few flags, a few particular flags, and these two key ones here are W_all and W_error. So this isn't wall and whereer. They're not valid words. This is saying birds are happy. This is saying all and error, and what this is actually saying here is it's saying, I think W_all is please let me know about all warnings. So W means warning, and all means like all of them. So tell me about all the warnings. And W_error means make all warnings an error. Because when you compile, there are two things that can happen, and I'll try and show you this. So like, if I just compile, let me add a new line here. It says like int a equals 5. When I compile this with GCC, I don't know. There's just the birds outside. They're not like, oh, hey, Larry, or anything. It's just birds. So when I run this, it works fine, right? Even though I've got this variable called a here, but I think this will be an error if I do W_all. So notice now when I try and actually compile this one with the W_all, which says give me all warnings, it will now say to me, warning unused variable a. So this is GCC doing it. You'll also notice that DCC does this without the W_all, right? And that's because DCC has these kinds of flags turned on by default. So it's kind of simpler for you to write this code because you don't have to add all these flags and stuff. But let's go back to what we had with this W_all here. One thing though is with the W_all, it will still compile. That's kind of the problem. So essentially it allows you to develop bad habits as you're programming, because now you say, oh, okay, this still compiled, I'll fix this later. And then you stop kind of reading messages and your code can become very unelegant very quickly. So if I was to say, change this to factorial 9 or factorial 6, right? And then I go to compile this and I run it, you'll see that it actually has compiled successfully. It's just given me a warning on the way of doing that. Whereas if I now change this to 4, for instance, and I compile with W_all, W_error, it will now fail to compile. You notice that warning has gone from warning to error. And now it's saying that I found a warning, I'm going to treat this as an error. So there you go. And now when I try and run it, it's still the old program because the new executable was not written. The compiler didn't actually override it. So I got some questions here which are, I already answered what's the benefit of warnings shown as errors. If we use wall and whereer, you call it wall and whereer, but I'm just saying it's not, you're not compiling with a wall, you're compiling with all warnings. If we used wall and whereer when compiling with DCC, what would happen? Well, I think it actually just does it. Like it's kind of like, it's already got the flag, so it's just like ignored because they're already set. And those flags are case sensitive, I think. I honestly, in my 8 years of doing this, I don't think I've ever tried. Yeah, they are case sensitive. So then the next question, which is really important, are we expected to compile our code without using wall or whereer? So no. You are expected to compile it with this line here, which has W_all and W_error in it, or wall and whereer. This is the standard compilation line we expect you to write in the course. GCC -W_all -W_error -O factorial 1.c. And to answer Joshua's question, why don't we use DCC, which is the question that was asked yesterday, that's because DCC is a CSE specific thing, and once you leave CSE and go into the real world, you're going to need to have to deal with how the real GCC actually works, right? Because it's like, think of it like training wheels, right? So it's like, why don't adults ride with training wheels on bicycles? Well, they probably could, but it maybe might slow you down and it might make you less robust for like dealing with a broader range of situations, right? And that's kind of why we're here, to help you take that next step up in your evolution, if you will. There's one other flag which we will talk about and you'll see around, which is -big O. This is the optimizer flag, and this one gets a bit complicated, but essentially you can include it, you can not include it. It doesn't really matter for small programs we write in this course, but the -big O flag usually tells the compiler, if you see ways to optimize this code, then please do so. sometimes like it might do something. I'll give you a really simple example, right? If you write some code that's like int I equals 0, or like if you write some code that's like int sum equals 0, for int I equals 0, I less than 100, I plus plus, sum plus equals I, the compiler, like smart compilers, if they're told to optimize things, might actually not even, like when it compiles that, it just might turn that into a number. Because it's like, well, I can actually figure this out at compile time. So rather than making a program that will run and just sum up all these numbers, I will just do it at compile time, right? Save you some time. That flag is something that won't have an impact in anything we really do. But you know, you'll see it, and we'll keep chatting about it. But the point is, this is what you definitely need, and sometimes you'll see a -o there as well. They wouldn't use something like DCC because it increases compile time, correct, and runtime. It makes runtime slower as well, which is really important. Probably compile time is probably less an issue because, like, you know, if things take longer to compile, then okay. As long as it makes the code safer, which you could argue DCC does, it's probably the runtime thing that's the bigger issue in the real world. Yeah, and some people have answered questions in the chat. Okie dokie. So anyway, this was a really long-winded explanation to compile this program. Bam. We're going to compile it, we're going to run it. We get 24 because that's what factorial 4 is. Now, okay, there you go. Now we're going to have a look at a recursive example. So I want to contrast these two things. So let's actually look at this for a while. And again, recursion won't always make sense straight away. And have a look at this right-hand side. What do you notice about it? So what you notice is that there's no for loop. That's what I kind of mean about these are in some ways alternatives to looping. And what this function actually does is essentially calls itself multiple times. So I just want to show you how this like might pan out in reality. So you can see that factorial here calls itself. So I actually wanted to get my drawing tablet up today, but I kind of didn't, so I'm sorry about that. But let me just get my snippy toolie, and we can copy and paste this into Paint here, and we can chat about it. So here's our really simple piece of code. Now let's actually trace through what happens here, right? We start off by on line 9 here calling factorial 8. Okay, and what happens when we call factorial 8? Well, we call this function up here. Now the first thing the function does is it checks is n, the input here, 0. No, it's not. So it's not going to enter that return 1 thing. Then it says, okay, well, if we're not doing that, I'm going to return n, which is 8, times by factorial of 8 minus 1, which is 7. So that's actually what the first call to the function does. The second call to the function, so that's that first call, we call it from main. But when this factorial function tries to return, it actually has to call another function called factorial. It has to call itself again. So what happens is that factorial here of 7 calls the factorial function. It says, okay, is n 0? No, it's not because it's 7. Then I'm going to return 7 times factorial of 6. Right, and then this kind of echoes on for a little while here, where we get, return 6 times factorial 5, and then I'm just going to write it over here just for like cleanliness sake, and then it's like, then returns 5 times factorial 4, and essentially these kind of keep calling each other, and that's why we call it recursion, because it's calling itself, right? Return times factorial 3, return 3 times factorial 2. I should have used a smaller example than 8. This is what happens when you write new lectures. You're like, oh, this makes sense, and then you think, oh, now you've had to write out all these examples, but we're committed now. So it kind of does this, right? Like every single time it finds this, it's like calling itself, recursively calling itself. Now what happens is we get to factorial 1 here, and it calls factorial of 1, n is not 0. So now what it does is it returns 1 times factorial 0. And then what happens with this one? What is factorial 0? Well, what factorial 0 is when you call factorial with n as 0, it actually just returns 1. So when I call factorial 0, it returns 1 here. Yes. And then what actually happens is, like, once it's got all that, it can actually fill in the gaps, right? And I kind of nearly wish I wrote this in Excel, so that I could show you like the flow a bit. But it's like similar thing here. If I call factorial, let's factorial 8. What is that one going to return? It returns 8 times 8 times like factorial 7. This might be my preferred way to explain it to you. So, and this would kind of ripple onwards like this, with like tons of different numbers, like this. I really regret choosing 8, but that's okay. We're nearly there. Factorial 3. This one's 3 times factorial 2. So this is actually what the computer does. It literally goes in and calls all of these different things until it finally gets down to factorial 0, which this one is 1. And then what happens is, once it's figured out what that value is, it says, oh, well, I know what factorial 0 is, it's 1. And then it says, well, 1 times 1 is 2. Okay, well, I know what factorial 1 is, it's 2. And then it says, well, 2 times 2 here is 4. I know what factorial 2 is, it's 4. 3 times 3 here is 12. I know factorial 3 is 12. 4 times 12 is 48. I know that factorial... Is factorial 4 48? I feel like I've done something wrong. No, I did a mistake. Sorry. Where did I screw up? Someone help me out. 1 times 1 is 2. Thank you. I was like, I'm pretty sure that 4 factorial is not 48. So factorial 1 is 2. This is now 4, so factorial 2 is 4. This is 12. What? What have I done wrong again? Have I screwed it up? Oh my god, what's wrong with my brain? Jesus Christ. Okay, so factorial 2 is 2. So we can replace that there. What's 3 times 6? It's 6. 3 times 2 is 6. Oh my god. 4 times 6 is 24. You get the point. This kind of like ripples all the way up to 120, right? And the point is that it all unwinds all the way back. I don't know what 7 times. I'm not okay. I'm absolutely not okay. I can't believe that I just like casually could remember most of the factorials off my head, but then I forgot that 1 times 1 is not 2. Thank you. So this becomes 5040, and then this one up here becomes, I think, 50, 30, 20, right? 40, 30, 20, nearly. So that becomes 40, 30, 20. Like that. Should have written a function in Excel. I absolutely should have. So that's kind of how it works, is you have to kind of understand the way recursion works is it essentially does kind of 2 sweeps. It does the first sweep, which is it goes down and like calculates all of these. So it actually has to call all these functions one at a time. And then when it finally gets to the bottom here and it finally figures out its value, it does what we call unwinding, which is where it then keeps returning them back up. So in actual fact, if you were to look at how these recursive functions work in memory, what would happen is it would call factorial 8, and then it will call factorial 7, and it would keep doing this all the way down till it calls factorial 1 and then factorial 0. And only when it calls factorial 0 does it actually give you a value, which would be 1. And now that it knows the answer is 1, it can like unwind, because then this one can return to the one above, and then this one can return to the one above, and then this one can return to the one above. I really like Trent's comment here, which is that it's just a different way of thinking. Give it some time and it'll eventually be just as easy to follow. So I think that's totally right. So recursion's one of those topics, a little bit like pointers, where some people get it instantly, Some people get it soon, some people it takes them a few weeks to get it. But a lot of the time, most people eventually get it. It's just a question of time. And everyone's brain has a different way of trying to think about this. Like, I've just explained this one way here. There'd be tons of things on the internet about it. I mean, I know just even like on WebCMS3, for instance, that we don't have a video for recursion, that's okay. But like in your tutor will talk about it, your tutor will explain it to you a certain way. We're going to go through some more examples now, for instance. But the point is that if you notice this, it's a little bit simpler to write because there's not as many loops and stuff. Now, a really important note here is that you can see that I've got these two phrases here, which is base case and recursive case. And these are two really important terms for recursion, because recursion by nature is a function calling itself. And if that function is totally identical every single time it's called, then it will essentially never stop, right? It will just keep going forever. So what we actually have is this idea of a base case, which is saying that there is a certain condition upon which, as it's recursing down, it eventually says, I'm done now. I've done enough, time to stop and time to unwind. So if you imagine recursion as this big digging a hole in the ground, recursively calling itself, the base case is the point where it says, stop, it's time to go back up now. And we can demonstrate a couple of these things. So firstly, let me take this, and we'll use this program here. Let's try and compile this one. Great, and then we'll run it. We get the same answer, that's what you'd expect. But what I want to do here is put in some print statements. So I'll call calling factorial %d. And so let's actually have a look at this. Let's watch this in action. So you can actually see how it works here is that we've actually called this function 8 times. Now this makes sense because this is what we've gone through previously. But let me actually just separate out this return statement here. I can make this a little bit even easier for you to read. So instead of having this very concise function here, let me just expand this out slightly. And I'll make it into an else if statement for you. So now we can see this is our base case. If n is 0, we want to return 1, because the factorial of 0 is 1. If it's not, then it's our recursive case, which is where we want to keep recursing down. Now, instead of returning 1 and returning n, I'm actually going to capture the return value. I'll call it int return value, and I will set return value to be either 1 or to be this. Right, and then I'm just going to return value. So this is very much like a 1511 kind of thing, where we're essentially trying to avoid multiple returns. And what I'm going to do is I'm going to put two printfs here, one up the top to say when we're calling the function, and then one at the bottom to say factorial whatever returns something, where I'll put return value here. So we can get a good sense of the actual flow through the program. Now here's what I want you to have a look at. Notice how that the program starts from 8 to 7 to 6 to 5 to 4 to 3 to 2 to 1 and 0, and then from here it's actually printing them out in reverse order. And that's because, again, another way I can get you all to think about it is that you got to think of recursion like, if we go back to the internet pictures I found, like this. This is kind of what it's like. You're building boxes within boxes. So, you know, this might be our factorial 8 here, and then inside that's our factorial 7, and then inside that's our factorial 6. And it goes all the way down to like factorial 1 or whatever in the middle. So if I just use a simpler example with simpler numbers, where we start off with like factorial 4, factorial 4 calls factorial 3, and what happens again is the order in which the program flows is it moves from the out to the in until it gets to the base case in the middle, which is what stops it just infinitely making more boxes inside itself. And then once it reaches this point, it finally has enough of a value. So it says, you know what, this box is number 1. Oops, that's a terrible one. This box is number 1. So then it can actually say, okay, I'm going to return that one, and goes back to 1, and then back to 2, and then back to 3, and then back to 4. Right, so if you want to think about it visually, it's essentially that process by which you're actually you know, making boxes inside of boxes and then moving back out once you have the answers. And that's what you can see here when we print it out, because you can see that it actually goes all the way into the bottom and then it starts returning the way back, building back up from the very bottom back up to the very top. Diora says, think of it like you're standing on a staircase. You go down 8 steps and only then can you come back up 8 steps, and you have to come back in the reverse direction. Yeah, so I'm just gonna have a look at a couple of the questions, because I saw people posting about this. Jay says, Jay's answering a question, which is like, recursion might be easier for some situations. So we'll learn this in week 3 when we look at trees. We're going to look at tree structures, which are essentially a huge, complicated version of linked lists. And that'll probably be the first time, in my opinion, that you'll see recursion and be like, oh, okay, this actually makes a huge amount of sense where it's easier. Waleed says there's a Mark Chi did a lecture on his channel, which you can go check out. Sounds good. Some other people have kind of answered things. A couple of people have been talking about performance. I won't talk about performance too much now because it's quite early on in the course, but typically speaking, recursion is... rarely is it faster, and certainly rarely does it use less memory. It's often a little bit of, if you will, it's a bit like a programming hack. It's like a cheat way to write complex logic in a simple form. It's certainly not necessarily going to make your program quicker, and that's a really important note to have. Yep, Waleed says it's not a feature of C. That's correct. It's a programming pattern. A recursion is like... well, I mean, it's kind of a language feature, because like some languages wouldn't allow it, but it's no like different to a function. Like, it's just something you can do with a language that you can do with many other languages. So conceptually, it's not specific to C. But yeah, I would not say that recursion is rarely that much slower per se. It just uses a lot more memory. And I'm not going to try and explain that right now, because I think we're already touching on quite a lot of ideas and topics. Chewy says, just to be clear, I just want to maybe clarify my previous comment. So it's nearly always going to be slower. My point is that it's in cases like this, you're not going to notice any real performance problem. Just because of the nature of the algorithm, but some cases you will. It's rarely better, but sometimes it's just negligibly worse. Lots of really interesting questions in the chat that I don't think we can get to. But again, Dicko's comment about, so essentially recursion is an ace up the sleeve used for specific scenarios where it's used to simplify an iterative process. Beautiful. That's a perfect description of it. So yeah, pretty much that's it. It's like, I'm just going to paste that into the thing because I like that. So this has been Dicko's takeaway from it, which I like. Big clap moment. How do we send? Can we send claps in the chat? Is that a thing you can do? Clap. Okay. Yeah. So I don't think there's a ton else. Oh, let's get rid of the base case. Let me show you that. So let's get rid of these. Yeah. Let's watch what happens when we get rid of the base case. If all we do is just do the recursive case all the time. Right, so you see this function here where we're basically always recursing. We don't have a base case. You'll see it will just go on forever till the program crashes. So it's just continually calling itself now with like n as -1, like it's just doing that. And it eventually segmentation faulted here. So I've heard some people ask questions about segmentation faults in the chat already. So a segmentation fault is essentially an error where you access memory you're not meant to. I posted about this on the forum. You can go and like look at that if you want. Kevin's answered some stuff, I've answered some stuff. But yeah, essentially it's like when you access memory you shouldn't. Common cases for that are accessing parts of an array you shouldn't, or dereferencing a null variable, trying to print out a value. But generally segmentation fault means you have touched memory, you have tried to access memory that you can't. The reason this program has done that is because it has run forever and it has eventually hit its RAM cap. So every program has allocated some memory on the computer, and the operating system has basically seen this thing take up more and more and more space, and then it's just been like, you need to stop now. So I'm just gonna not let you touch any more memory. So it's just said no more, and then the program's just crapped its pants. Okay. All right, so let's get into that's a good example to start. Let's keep going through the examples. So factorial is kind of the classic recursion example because it's really digestible. But a much better example to like really explain the benefits of it is a Fibonacci. Sorry, there's a couple of imperfections on this one. That includes the page title. Sorry about that. New slides. I'm making new slides this term for some topics, so just a couple of little hiccups. So this is Fibonacci. So if you're familiar with Fibonacci numbers, I'll just give you a quick recap because I'm sure there's 5 or 10% of you who aren't familiar with it. These are Fibonacci numbers, not really. That's probably Fibonacci, I guess. Or I don't know. I don't really know what Fibonacci looks like. But Fibonacci numbers, you probably did this in high school. It's essentially things like this, where if you sum up two numbers, 1 and 1, you get 2, and then if you take 2 and 1 of the previous numbers, you get 3, and then if you take 3 and 2, you get 5, and if you take 5 and 3, you get 8, and if you take 5 and 8, you get 13, and if you take 13 and 8, you get 21. So it's essentially where the next number is the sum of the two previous numbers. So you could write the sequence out pretty easily. You could probably do it in Excel actually. If I say 1 and 1 as my first two numbers here, and then I could say that this number is the sum of the previous two, and then this number is the sum of the previous two, and you could kind of just do that forever. Like there are the Fibonacci numbers. We just did it in Excel in like 2 seconds and one formula. So if we want to write a program to actually so I just closed the chat for a second and people are talking about hats. I use Microsoft Edge because I couldn't be bothered installing Chrome, and I only use this for lectures so that you don't see me Googling stupid things like why are cats and dogs not friends or something. And I can just so there are Fibonacci numbers. How do we calculate that in C? Well, the iterative approach is actually really complicated, and in fact it's complicated enough that I didn't write this because it confuses me, and I found it on the internet, and it's a standard algorithm. It's not like it's some genius thing. It's pretty much just an iterative solution that uses for loops to figure out what all those numbers are. And it kind of does so if you look at the program, and we don't need to think about it too hard, but it essentially keeps track of the current number, the previous number, and the previous number. So it's like the current one, the previous one, and the previous one, like that, right? And that actually makes sense because that's what our program here was doing. We were keeping track of our current number with respect to the previous one and the previous one. And then we were moving all those down by 1. So this is our new current number with the previous and the previous. And that's all this iterative program is doing here. So iterative solution, kind of ugly. If you asked me to write an iterative solution to Fibonacci, it would probably take me, I don't know, probably 10 or 15 minutes to figure it out. If I couldn't Google it, I'd be like, oh God, how does that even work? And there'd probably be some bugs in it anyway. So what you'll notice though is if we look at the recursive case of this, it's actually much more simply defined. Because remember how, the thing about recursion, I think, is that recursive solutions are honestly often just the literal expressions of you describing a problem to someone. So in the case of the Fibonacci sequence, when I say to you, this number in the Fibonacci sequence is literally just the sum of the previous two numbers. And then the previous two numbers are just the sum of those previous two numbers. You can actually write that out quite literally like this. You can say that the Fibonacci, like let me just be clear. So what this Fibonacci function is actually doing, this is why you should comment your code, because this one won't make sense if you don't think about it, is it's saying find me the first 3 Fibonacci numbers. So when I call Fibonacci of 3, I think it's finding me 3. So in this one, the 8, it's going to find me the first 8 Fibonacci numbers. So what it's saying here is that, well, if I try and run this, I'm just going to skip the iterative example because I think that it might be easier just to look at this one. Let's try it out for Fibonacci of 1. Well, like, find me the first Fibonacci number. Okay, well, I'm just going to rename the file so that it's definitely not confusing for anyone. I'm going to call it fib.c. I'm going to compile fib.c. Then we're going to run fib. And it says, let me do it for number 1. It says 1. So I want 1 Fibonacci number. Now that makes sense. That's pretty consistent with our Excel. 1, 2, 3, 4, 5, 6, 7, 8. So this is what we'd expect. 1 Fibonacci number is 1. The second Fibonacci number is 1. The third Fibonacci number is 2. The fourth one's 3. The fifth one's 5. The sixth one's 8. The seventh one's 13, etc. So let's find this. Now let's make this even better. Rather than printf the Fibonacci of 1, let's actually scanf something in really quick. Say, which fib element do you want? Like that. And then we'll just scanf it into a variable. We'll call that variable element. And then we'll say scanf %d element, like that. And then we'll just pass that into the function. That way we don't have to recompile it all the time. Okay, so now I run it. Which fib element do you want? 1. Which fib element do you want? 2. And 3. Now let's have a look at these 3 cases here. So when I pass in fib element of 1, what actually happens structurally is that I call Fibonacci of 1. And what does that do? Well, it checks if n is 1, and then it immediately returns 1. So that one's immediately 1, and then the function just returns. Pretty simple. When I call it with 2, though, what happens is that I call Fibonacci of 2, and then it's not, n is not 0, n is not 1, but instead what it says is I'd like to now, the value of this is return Fibonacci of 1 plus Fibonacci of 0, right? Because that's what it's defined as. But then what's the value of Fibonacci of 1? 1, and what's the value of Fibonacci of 0? 0, right? Because in this case, that's what the base cases are. That's what stops it looping infinitely, right? Because otherwise it would just keep calling itself forever. There's nothing to say, all right, this is the point where you stop. So we would do that, and what do these return? Well, Fibonacci of 1 gives us 1, and Fibonacci of 0 gives us 0. So that's what they would return as, and then that would return as 1, which means the Fibonacci of 2 is 1, which is consistent with what we have here. And then when we do 3, or maybe let me just show you 4, Fibonacci of 4, what happens here? Well, 4 is not 0 or 1. So this actually returns, I'm just going to use fib to be quicker. So this one returns fib of 3 plus fib of 2. Okay, well, what's fib of 3? Fib of 3 is we return fib of 2 plus fib of 1. And then what's fib of 2? Well, we return fib of 1 plus fib of 0. Right? Like, and this kind of goes on forever. Now, Fibonacci is a really interesting case, and I actually want to maybe draw this one up because I want to show you how algorithms like this actually are a lot more complicated in terms of the amount of memory they use. So the first thing is if I say Fibonacci of 4, which is defined as Fibonacci of 3 plus Fibonacci of 2, what the program actually does when it runs here is it takes this over here and it says, well, I know that the fib of 3 is equal to the fib of 2 plus the fib of 1. And then it takes the second component over here later. Well, technically speaking, what it will do is it'll actually do it in this order. It'll always kind of keep going down the left-hand side here. And it'll say, well, I know that fib 2 is equal to fib 1 plus fib 0. And then it will take this one and it will say, well, I know that fib 1 is equal to 1, right? Because that's a base case. So that's where it stops. Then it'll take fib 0, which it knows is 0, and that's another base case, which it'll take there, like that. Then it'll take fib 1 here, come down here, and it'll say fib 1 equals 1, because it's a base case. And then it's going to take fib 2 over here, and it will say, as you'd expect, fib 2 equals fib 1 plus fib 0. And then these two things were nearly there. Fib 0. Now notice this. I want you to notice something. Notice how much repetition is involved here. This was already calculated over here. This was calculated 3 times, fib 1. Fib 0 was calculated twice. So we actually have a lot of redundant calculations here because recursion structurally is very... What is that? Oh my god, that's a glitch. Recursion structurally very simple. It's not like hyper aware. Someone asked previously, could I cache these results? Could I store all the results to make it process quicker? Yes. You probably wouldn't use recursion in that case then. If you care enough about that, you probably wouldn't be using this method because this is very simple to write and very poor to perform in this case. You could still, but anyway, let's not complicate it too much yet. So very inefficient. And what you would notice is this grows, the ugliness of this grows really dramatically, really quickly. So if I was to say fib 5, the size of this would like more than double. It would like just massively grows out. It would grow out exponentially. And you can actually see this when we run this program. Let's run this program with a bunch of different numbers and notice how long it takes in many of these instances. So if I do 4, 5, 6, it's okay here. But let's try like 15, maybe 50. Real slow. So this is going to be a prelude to the next lecture, and I think it's a really interesting use case. So with Linux, if we do like fib of 3 like that, we can actually time how long that program takes to run by putting the time command in front of it. Now this is something we're going to be doing in the next lecture, so I'll introduce this again. But if you run a program and then you run it again, but you put the time in front, it'll actually tell you how long it takes, right? So we'll come back to this, but in the meantime, I just want you to focus on this real number here. Now, what I'm going to do for simplicity is I'm just going to put a number here called input, and this number might be 3. So instead of running fib and entering 3, I'm actually going to run fib and just pass in input. Pipe it in. I hope to God they still teach you that in 1511. I'm sure they do. So that's how we can see. If we want to do 4, I'll just update that file and run it again. If I want to do 5, I'll just update that file and run it again. And we can start to see how long these things take. So if I put time, you literally just write time in front of this command. Do they not? I hope they do. Anyway. Well, it's in the lab this week. Okay. Well, I don't know whether they do or not. You probably all did it in different things, and it's in the lab this week. But just to level it out for everyone, because it's a pretty important thing. Essentially, when you run a program like fib, it's waiting for command inputs, right? It's waiting for you to type something. I type 5. If you run a command like fib, but you instead use the side arrow and you give it the name of a file, it'll take the contents of that file and it will pass it in as if you're typing it on the keyboard. So now instead of me having to type 5, I'm basically sending a file with my keyboard commands into it. So now it does that for me. So this 5 you see here is actually the output 5. So when I make this like 10 or something, it'll actually you won't actually see it written, but it says like 55 because that's what the Fibonacci of the 10th Fibonacci number is. But what I want to show you here is if I put a time in front of this, this will like how would you put it? Time my program. It says that it took 2 milliseconds. And if I change this to like 12, it takes 2 milliseconds. And if I change it to 20, it takes 2 milliseconds. And, you know, the computers are really fast, right? They're really, 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 really fast. But notice when I go up to the 30th Fibonacci number, it now takes 16 milliseconds. And then when we go to 31, it's going to take 20. And when we go to 35, it takes 74 milliseconds. And when we go to 40, it takes 700 milliseconds, or like 0.7 seconds. And we'll go to 41, and it suddenly goes from 0.7 seconds to 1.5, and then very quickly it starts to take a lot longer. Right now we're at 1.8. 3 seconds. If I go straight to 45, it's taking quite a while, right? This is only 2 extra numbers. It's gone from 3 to 7 seconds. 47 takes a lot longer, and the very nature of this particular thing is it's gonna be like an exponential. That was the worst explanation of an exponential I've ever done, so I'm just gonna Google it. It's basically something that just like gets out of hand, right? We all know what exponentials are from high school, but like it's all tame until it's not, right? It's fine, and then it's not, and then it's really not okay. And that one ended up taking 20 seconds. And very quickly this would be out of control. And honestly, the reason that we'd probably see it break eventually is because it's taking a long time, because it's having to call all of those functions, and all of those functions are taking up memory. So eventually it's probably going to run out of RAM before it stops processing. Because if you were to do something like the Fibonacci of 100, that would probably take like many gigabytes of RAM to calculate recursively. But let me just show you the magic here. For 45, it takes, for the 45th Fibonacci number, the recursive algorithm takes 7 seconds, right? But let me do the iterative one. When I do the iterative Fibonacci, and I compile this one again, and then I run this one, it takes 3 milliseconds, right? 3 milliseconds to run, as opposed to 7,884 milliseconds. That's massive. And the reason for that is pretty simple. The nature of recursion is that it's a function that calls a function, and they just ripple out in that direction. The reason our factorial one was pretty quick was because it was kind of a linear thing, right? You're just like going bam, 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 like that. Whereas in the case of Fibonacci, it's like every single function calls 2 more, and then each of those call 2 more, and then each of those call 2 more, which basically means that effectively, right, it's like 2 to the power of n. It's like 2 to the power of something, because it's like constantly calling, like, you know, the first one calls 2, which calls 4, which calls 8, which calls 16, which calls 32, etc. Oh, thank you. Sorry. So Diora has picked up on that I didn't modify this program, so we will have to do this one. It still will be really quick though. 0.3 seconds, yeah. So thank you, Diora. You're right that this program didn't scanf, so when I overwrote the file, I removed the stuff that we wrote here, which meant that we weren't actually reading from the file on my first run. You're right, we did the Fibonacci of 8, but you'll see that when I recompiled it, it still took literally no time at all. And in fact, if we tried to do something like this, which, just to be clear, this won't work because integers are not big enough on a computer to handle numbers this big, but if we did this, it's also nearly instant. Okay, so a couple of questions from this. Harry says, is there a reason why you use argc and argv even though you aren't inputting any extra arguments? That's just a habit I have. I honestly don't remember whether it was in the style guide or not, and I've just written it in just in case it was. Some other questions we'll answer later. Cool. So, point of this, what's the takeaways from this example? Recursive programs for a number of scenarios can be easier to write. They can also be a lot slower to run because they have to create functions for every call. So particularly speaking, if your recursive function calls itself multiple times before it returns, then there's a good chance that as the input size grows, your program will run a lot slower than the iterative version. Though the iterative versions are much harder to write. So this one is harder to write. It doesn't make a lot of sense. Like, you know, like I know what this does, right? But when I first kind of saw it, I was like, I got to figure out what this is doing, draw it out a little bit. But it's really quick. So, and this is a big theme we're going to keep coming back to in this course, which is like, what's the right approach here? Is recursion better? Is iteration better? Depends. What are you doing, right? Like, are you always going to be, do you know all the Fibonacci numbers you're looking up are going to be like less than 12? Yes? Well, then why wouldn't you use recursion? It's plenty fast. It's the same speed as the other one, and it's a lot quicker to write. It's a lot quicker to understand. Are you going to be finding large Fibonacci numbers? Maybe. Well, then you should probably use the iteration one, right? So it's all about making the right decisions. Jay says, would my computer crash if I did Fibonacci of 5,000? Probably not. We might chat more about this, but generally speaking, it's running out of stack memory, and the operating system will kill it. It'll kill it. It'll essentially see, wow, this program's going wild. I'll just end this now. That's probably happened sometimes on your computer. If you ever notice you have a program and then it just like crashes randomly, sometimes it can be because of a memory error or something like that. So we should have a break in a sec, and we can talk about linked list recursion briefly, and then we'll maybe start moving on to the other lecture. But let me just see if there's some other lingering questions. Anyone who's asking about timing, I'm not going to answer those questions yet because we are going to chat about it in the next lecture. So we won't answer about timing. I think everything else has been answered, but I'm hoping this gives you a bit of an insight into recursion. Generally speaking, like what I would say with recursion is that the use cases for recursion are sufficiently low that it's unlikely that you'll come across a common problem and be like, I should use recursion for this. Like most of the cases that I still would use recursion today are like some fairly basic common problems that I came across at uni. So don't think that you can go out there and apply this to like absolutely everything, because you probably just won't have a need to do that. But anyway, let's take a 5-ish minute break, and then we will do the last part of these slides. Sorry, I keep bumping everything. And then we'll move on to the starter performance analysis and get ourselves a head start on week 2, which will just take the pressure off next week. Don't stress, we can always just finish next week early too. It's just good to be cautious. So great, thanks everyone. Let's 5-minute break and then we'll be back. Okay, so we were pretty much at the end of this this beat slides. We kind of answered all these questions about whether it's faster or slower. Yeah, it gets complicated. The bigger courses are probably more obvious. Sorry, quick tangent. But if we have a look, like this question about is it faster or slower, does it use more or less memory? So it nearly always uses more memory, right? Nearly always. Is it faster or slower? It's usually slower, but as I said before, it's more complicated because most of its slowness comes from the same reason its memory is used, which is back to that paint thing we drew, which is like this. So it's slow by virtue of the fact that not the like the logic is necessarily slower. It's more that, I mean, I guess it is, but it's more that like for multi-part recursion, the branching factors can be pretty huge, which means sometimes you're double calculating things, and there's a bit of a cost to like adding to the stack frame and stuff. But generally speaking, again, you wouldn't use recursion to speed up your code. That's the main takeaway you should have from this. Now, the last thing here, and I decided that I didn't want to like go through an extensive example with this. We could if you'd like to, but what I wanted to show you was some more contrasts with recursion and not recursion. Which again, this is like my luck today is profound, managing to find one small mistake in like every single darn slide. Pretend you didn't know what it was. Yep, there it is. Okay, so essentially, if you go and look at like what you might have done for 1511, right? Like if you had a linked list, right? This is all about linked lists, which I'm hoping you remember. If you don't, you can go revise the linked list content we linked in the first lecture. But essentially, if you got given the head of a linked list, so just to be clear, sorry to stop again. We can't really go over linked lists because you spent time on it in another course, and the whole point of like doing other courses is to like we're not going to revise it extensively because we've already given you some materials, and that's why it's a prereq for this course, because we understand that you assume it. We will keep talking about it. I'm just saying we're not going to go back to like the basics of it, but we will be talking about linked list structures like next week, for instance, and then the week after that, and then probably the week after that. So it will keep coming up, and we might go through it today too, but generally I can't really guarantee anything. This is what like a 1511 length of a linked list looks like. If you have a pointer to the head of a linked list, and if we maybe just get a linked list structure up on Google so you can visualize it. If we have a pointer to the head of a linked list like this is a nice little diagram, right? You have your element, they all like point to each other. You can find the length of that simply by creating a current variable, which is your current pointer to it, and maybe we can do that quickly here. I'll just copy that image into paint, make it really big. So we can create ourselves a current pointer, which is some kind of pointer to it, and we can start off and we can point that to this here. Let me just get the slide up. Perfect. We point it there. That's what this is here. Current is pointing to the head. We say that the length is 0. And then while current does not point to null, we move it from this current node to what the current points to next. So we move it to there. And then we increment counter, or length in this case, sorry. So that's kind of how we count a linked list in like a 1511 style thing. We use a while loop. We go through it until we end up pointing to null at the end, and then we stop. So in this case, it's like, all right, current points there, length is 0. Is the next one null? No. So pointed here, length is now 1. Is the next one null? No. Pointed here, length is 2. And then pointed here, and the length is 3, right? Well, length is 4, right? We started at no, it'll do the fourth one here, sorry, yeah. So at this point, the length would be 3. And then the next one, it would still go here, but the length would be 4, and then, yeah. That was a bad explanation, but visually it's all the same thing. Length shouldn't start at 1 because someone might pass in null into the function. That's where I tripped up on my own thoughts. I was like, oh, should length be 1? But the problem is if someone passes null in as the head, then the length is 0. So you could still set it to be 1 and then do a check and then return 0, but that would make the logic kind of confusing. So this one's kind of easier because it basically it increases the length by 1 every time it makes a step. So it's actually like this is where it says 1, and then this is where it says 2, and that's where it says 3, and that's where it says 4. And then once it sees that where the current's at is null, it's like, oh, I'm done, time to leave. Oh, sorry, Chewy, I misunderstood you. My bad. Please forgive. We then have a 2521 version of linked list iteration, which is the same thing. It's just I've written it in a for loop. Some people might prefer this. Some people might say it's ugly. Personally, I think it's a little bit cleaner if you use the type def here, because for loops are kind of obvious to people. It's like, okay, a for loop. We start, we go until we increment. Like, I get it. It's all packaged right there because the statements have context, and those statements having context makes it much quicker to read. Yes, you're right. Sorry. Yes. Thank you again for pointing out a slight problem in the slides. I appreciate it. Sorry that there's been a couple of errors. Again, you guys are the first ones to see these, and I double checked them, but I missed 1 or 2 things. So I just removed the current equals current dash next. Thank you, Waleed, for picking up on that for me. Oh, Tawaka, sorry. Did Tawaka say that? Thank you. Thank you, Waleed, for passing on Tawaka's excellent insight. Cool. So basically this one's just like using for loops. It's the same thing. It's kind of a little bit simpler in a way, right? It's nearly easier to pick up on that. The recursive way to do it is to simply do this, and I hope that this kind of makes sense, because it's a lot like the factorial question we did. Remember how factorial was like, the factorial of 8 is just 8 times the factorial of 7, and factorial of 7 is just 7 times the factorial of 6. So in a lot of ways, what I can actually use the same diagram here, but what the recursive version of this is doing is it's simply saying, if someone gives me a pointer that points to null, then I'm going to return 0. Otherwise, I'm going to return 1 plus the length of the next elements. So what actually ends up happening here is that you end up kind of recursively calling it on like subsequent versions of it, which I can try and visually show you here. Is it raining for anyone else? The rain's really pretty today. I like rain. Except I have to go pick up groceries later, so I'm gonna get wet. Cool. So like, what actually happens here is when you first call length recursive, you call it with the head. You call it like with this pointer here. And then what it does is it says, oh, is head null? No. So we're not going to enter that. So it says, okay, well, the length of this particular node here is exactly 1 plus the length of this. Okay, and then we say, okay, well, what's the length of this, right? Remember when we say this linked list, we're simply referring to a pointer to the beginning of it. So what's the length of this linked list? Well, the answer is, well, it's not null, right? So the answer is 1. It's a very janky one. Plus the length of this linked list. And what is this linked list? Well, its length is 1 plus the length of this linked list. And this one is 1 plus the length of this linked list. And as you know, when we try and find the length of a linked list that is null, as in the head of the linked list points to null, it's 0. Because that's what we do, we return 0. That's the base case. That is the base case, and the return 1 plus length recursive is the recursive case. One thing I probably forgot to mention before is, if it wasn't obvious, the recursive case is typically the one that does the recursion. Right, the base case is typically the one that does not do the recursion. That one's pretty obvious. So then so this would call recursively. It would call like for subsequently smaller lists, and then when it finally gets to the bottom of all of these, once it all goes all the way down here, it would then have time to. It would then unwind. It would come all the way back up here, and as it comes up, it would say, okay, 0 plus 1 plus 1 plus 1 plus 1, and these 4 ones here would give us 4. So the answer would be 4. And that's the flow in which a recursive length one looks up. Now the cool thing about linked lists is that you can actually use recursion on quite a lot of solutions. You can use it on like deleting a list node, inserting a list node. I think length is the simplest example because length is already quite a simple function anyway. Yeah, so that's pretty much it on recursion. I think I just wanted to maybe take the opportunity to ask the people that are here we will talk about makefiles too briefly, but is there any other kinds of topics that we want to chat about? Because we'll keep coming back to recursion, I promise. Like, this isn't like, oh, this is everything you need to know. We'll keep chatting about it, but like Is there anything people are kind of curious about in the context of this before we maybe move on to a little bit of the next lecture? Anything people think we really need to kind of maybe revise or go into more depth with? Yeah, just in the context of recursion or anything we've talked about today. We can move. Yeah, there'll be more examples. Remember, you have tutes and labs and stuff, and we can always spend some extra time covering it again next week. So, can we do time command on those recursive examples? You can. I can't run this code because this code requires more linked list code, which I just don't have here. Like it requires us to make linked lists and stuff, and I mainly left that out because it's just a lot of code. Like, you remember linked lists, you got to like write the code to make it and do this, and we're going to talk more about linked lists next week, which will, I think, reinforce it. But yeah, so great. That's it. So last thing, I just want to show you makefiles one more time because people were like a bit confused about that. So as you've seen here, I've been compiling some code like this, right? We've got our fib code. I'll just make a quick makefile for you. So we're like, okay, sweet. Now, I'll tell you the truth. How do I make makefiles? I open a file. I save it called makefile, no file extension. And then to start writing the file, I go and find a previous example because I never remember how to write makefiles. And that's how I would encourage you to do it too. So I'm literally going to go, I mean, I probably could now because I had to prepare for the lecture, but like, generally speaking, if this was just a random day of the week, I'd be like, I don't know, and then I just go and find a random one like this. So I'd be like, oh, that looks nice. You can find these on the internet. It's such a simple markup framework that like you would really easily just like, they're all going to look the same. Oh no, that was weird. Portrait front. Okay, perfect. So here's our makefile, right? Now, the one thing about makefiles is that you always have this clean thing at the bottom, and the clean thing is just a remove all the .o files and then remove the final binary that you're building. Now, in this case, it's actually really simple what we're doing because we're only using one file. So I'll show you how you make a makefile for just one file. I would say that the executable we want to finish with, which is what we start with up the top, is called fib. And then fib is going to compile with, say, just one file, which is fib.c. And then we have our GCC command, which will be gcc wall werror -o fib for fib.c. So we're literally just writing our GCC command here. And what the makefile is saying is it's saying compile fib if you've seen changes to fib.c. So if we change fib.c, it will recompile it, and it will use this command to recompile it. So I'll show you. If I go make now, it will scan through this file, and it will say fib is up to date. It's basically like, sorry, but it's like nothing has changed since then. Kaustub says, why would you remove fib? Isn't that what you want to run? So you would only really remove it if you're trying to maybe like clean all the files and start again. So if I ls here, you'll see that I've got, you know, makefile factorial 1.c, fib and stuff. But rather than just like rming fib, I can just do make clean, and it will remove fib for me, like give me a fresh start. Like if I want to recompile it all again. So because I've removed fib now, when I go to make, it will actually compile it for me. So make does that compiling for me. So if you just want to keep running your GCC command, you don't even need to like copy and paste it. You can just like make a makefile that's literally just this. It's just you put that line in, and then you add, you know, the executable, the file name you're compiling, and then the clean. Yeah, so the clean isn't always run. It's run when you run make clean. So when I just run make here, it's like it's always up to date. And then if I go and modify fib.c to maybe be like 100, and I run make again, it will recompile it because it's changed. But then when I run make, it says it's up to date. What happens if you have two make files in one directory? I don't know, I've never tried that before. I'm sure it'll complain. Oh, well, you can't. Sorry. It's only ever going to look for a file called make file. You can't have two, but that's a great question. Yeah, so, and the point is that when you start compiling with multiple files, and I'll just really quickly show you this here, if I say extract this stuff out here into another file called like, call this one fiblib.c, right? Where let's say they both share a .h file. I'll include fib.h or something, and that fib.h is just going to be the prototype. Right, so now we've got a few files here, which is just like fib.h is just the prototype, fiblib.c is actually where it's defined, right? That's where the function is defined, and then fib.c is where it's actually run. So again, what this means now is that we could compile these two separately. So I could say gcc-wall-where-c fib.c, and this would output a fib.o for me. I could do the same thing for fiblib, which would output a fiblib.o, and then if I want to link them together, I would link them together. And this comes back to what we talked about yesterday. In the slides where we said like this thing here. So we take our C files, they all get turned into .o files, and then we join them all together at the end. So if I was to split this up, I would now have to update my make file. And what my make file would then say is that fib is actually made up of compiling fib.o and fiblib.o. So I'd need to update this. And then I also need to specify how these two files are compiled. So now I'd say, well, fib.o is compiled by compiling fib.c, which is gcc wall where o fib. Oh, I could just say this, I guess, because -c means compile but don't link. And then I could do the same thing for fiblib, like that. And then I think this would all work if I just ran make. Yeah, so it sees I haven't modified the file, right? If I do like 1,000, will this update? Yeah, so that, but like again, what you'll notice here is that it only recompiled fib.c. It did not recompile fiblib.c because the fiblib.c part's already been recompiled, like it hasn't changed. So rather than like recompile every file, we only have to recompile the ones we've changed, and then we link them together at the end. So the linking always happens, but we only have to recompile what actually changed. Anyway, that is the end of recursion. Let's do the old feedbacky thing. I'll put this up for a minute. If you could just share some feedback on this. Damjan says, do you need to put the .h file in the input part of the make file to make sure you recompile it? No. So the .h file is included as part of the .c file. That's what the include is for. So with the include here, this is how the compiler knows to include it. Jay says, do we ever need to split the compiling process into .o and .c files? So you do need to, if you would like it to be proper. Because what splitting that up allows you to do is it basically allows you to separate out the compiling and the linking stage. So it like if you didn't do that, it would still work fine. It's just that it would always recompile everything, which would just kind of somewhat defeat the purpose of the make file generally. Zach, I don't think we might go over that later. I don't think that's a core part of the course, but I'll double check that stuff. Okay, well, thank you. Let's wrap that up.